Preparing for a quantum hardware engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What do T1 and T2 mean for a physical qubit, and how would you measure them? Qubit coherence describes how long a physical qubit preserves phase and energy information. I separate T1, energy relaxation, from T2, dephasing, because they point to different failure mechanisms. In hardware work, I measure them with inversion recovery, Ramsey and echo experiments, then connect results to materials loss, flux noise, thermal photons, or control leakage. Good answers also explain that gate fidelity is bounded by coherence, but often limited by calibration and crosstalk. While answering, focus on physical meaning of T1, T2, common measurement sequences, dominant decoherence mechanisms, and how coherence relates to gate fidelity, materials, packaging, and calibration decisions. Question 2. Walk me through how you would calibrate a single-qubit gate on a superconducting qubit. A single-qubit gate is implemented by a shaped microwave pulse resonant with the qubit transition. I would first characterize the qubit frequency, then calibrate amplitude for a pi and pi/2 rotation using Rabi experiments. Next, I tune pulse length, drag coefficient, detuning, and phase to reduce leakage and quadrature errors. Finally, I validate with randomized benchmarking or gate-set tomography. Then monitor drift, because cryogenic systems and qubit frequencies move over time. Make sure to cover pulse-based implementation, Rabi calibration, pi and pi/2 rotations, drag, leakage suppression, phase control, validation with benchmarking, and calibration drift over time. Question 3. How does qubit readout work, and what limits readout fidelity? Readout converts a qubit state into a classical voltage without destroying useful statistics. In a superconducting platform, the qubit shifts a resonator frequency, and a microwave probe picks up a state-dependent phase and amplitude. The signal passes through a parametric amplifier, cryogenic HEMT, mixers, ADCs, then classification software. I optimize probe power, integration time, resonator line width, and amplifier gain. The trade-off is speed and separation versus measurement-induced transitions, heating, and crosstalk. In your answer, talk about dispersive readout, resonator coupling, amplification chain, signal-to-noise ratio, assignment fidelity, QND behavior, integration time, measurement-induced errors, classification methods, and trade-offs. Question 4. How would you detect and mitigate crosstalk in a multi-qubit device? Crosstalk is dangerous because calibrating one qubit can quietly break its neighbors. I look for it by running simultaneous RB, spectator Ramsey, frequency shift scans, and conditional error measurements. Sources include microwave leakage, shared control lines, package modes, flux line coupling, and resonator collisions. Mitigation can mean better filtering and grounding, pulse pre-distortion, scheduling constraints, frequency allocation, tunable coupler bias optimization, or compensation pulses. I always distinguish static frequency crowding from dynamic pulse-induced effects. Be sure to mention how to detect crosstalk experimentally. Distinguish static from dynamic effects. Identify electromagnetic or control line sources, and mitigate through layout, filtering, compensation scheduling, and calibration. Question 5. A qubit's T1 suddenly drops after a cooldown. How would you debug it? When T1 drops, I treat it like a hardware fault tree, not just a bad data point. I first confirm measurement repeatability, temperature, attenuation, and readout power. Then I check qubit frequency dependence, because TLS defects often create sharp loss features. I also inspect flux bias, infrared shielding, quasi-particle poisoning, package modes, and recent cooldown or wiring changes. If neighboring devices change too, I suspect system-level noise. If only one qubit changed, I suspect local material or fabrication defects. While answering, structure it as a debugging flow covering measurement sanity checks, environmental changes, frequency-dependent loss, TLS defects, quasi-particles, package modes, cryogenic issues, and system versus local diagnosis. Question 6. Compare superconducting qubits and trapped ion qubits from a hardware engineering perspective. Superconducting qubits are lithographically fabricated circuits controlled by microwave pulses at millikelvin temperatures. They offer fast gates and integration with chip fabrication, but coherence, wiring density, and crosstalk are hard. Trapped ions use atomic states with excellent uniformity and long coherence, controlled by lasers or microwaves. But gates are slower, and optical systems are complex. I would not call one universally better. The right platform depends on scaling architecture, error correction overhead, manufacturability, and control complexity. Make sure to compare platforms by control method, coherence, gate speed, fabrication maturity, uniformity, scaling path, cryogenics or optics complexity, and implications for error correction. Question 7. What cryogenic design issues matter most when operating quantum processors? At millikelvin temperatures, tiny heat loads matter. I budget conductive heat through coax, DC wiring, supports, and radiation. Then use attenuators, filters, thermal anchoring, and infrared shielding at the right temperature stages. For qubit control, attenuation reduces room temperature noise but adds heat, so placement is deliberate. I also care about magnetic shielding, ground loops, vacuum integrity, vibration, and cooldown repeatability. A beautiful chip can fail if the fridge wiring and packaging are noisy. In your answer, cover heat load budgeting, attenuation placement, filtering, thermal anchoring, radiation shielding, magnetic shielding, vibration, grounding, and why cryogenic wiring can limit qubit performance. Question 8. How would you design an automated calibration workflow for a many-qubit processor? Manual calibration does not scale past a small chip. I build a dependency graph. Resonator spectroscopy, qubit spectroscopy, Rabi, Ramsey, drag, two-qubit gates, readout, then validation. Each node has fit quality checks, bounds, rollback, and drift triggers. For many qubits, I parallelize compatible experiments while avoiding crosstalk and frequency collisions. The key is not just running scripts, it is designing robust calibration logic that knows when data is untrustworthy. Be sure to mention calibration dependency graphs, automated fitting, quality checks, rollback, drift detection, experiment parallelization, crosstalk-aware scheduling, and why robust automation matters for scaling. Question 9. How would you calibrate and validate a two-qubit entangling gate? A two-qubit gate is where hardware constraints become very visible. For a tunable coupler CZ, I characterize qubit and coupler spectra, choose an operating bias, calibrate pulse amplitude and duration, then shape edges to avoid leakage. I measure conditional phase, leakage, and population transfer, then refine with interleaved RB, cycle benchmarking, or cross-entropy style tests. The best calibration balances high entangling rate against sensitivity to flux noise, residual ZZ coupling, and spectator errors. While answering, cover the chosen gate mechanism, spectral characterization, pulse shaping, conditional phase calibration, leakage, residual ZZ, spectator effects, benchmarking methods, and speed versus noise trade-offs clearly. Question 10. How do fabrication and materials choices affect qubit coherence and yield? Fabrication affects coherence through every interface the electric field touches. In superconducting circuits, lossy oxides, resist residue, rough metal edges, substrate defects, and junction variability can all create dielectric loss or two-level systems. I would examine materials stack, surface cleaning, etch chemistry, liftoff, annealing, junction oxidation, and packaging. The practical answer is to connect process changes to measurable metrics: resonator Q, junction resistance spread, TLS density, qubit yield, frequency targeting, and cooldown to cooldown stability. Make sure to connect fabrication steps to coherence outcomes, including substrate preparation, surface oxides, resist residue, junction variation, etch damage, dielectric loss, TLS defects, packaging, yield, and metrology. Question 11. Your readout assignment fidelity is below target. What improvements would you investigate? Readout fidelity is a full chain optimization problem. I would start by separating errors, state preparation, relaxation during measurement, amplifier noise, resonator overlap, leakage states, and classifier mistakes. Then, I tune resonator frequency, line width, probe power, integration window, and parametric amplifier bias. On the software side, I use IQ calibration, matched filtering, and confusion matrix correction. Pushing harder improves signal-to-noise, but it can also induce transitions or heat the chip, so I validate QND behavior. In your answer, break down readout errors into preparation, relaxation, amplifier noise, resonator overlap, classifier limits, leakage states, then explain hardware and signal processing improvements, trade-offs. Question 12. What packaging and chip layout factors become critical as quantum processors scale? Scaling quantum hardware is partly an electromagnetic packaging problem. I look at mode density, impedance control, ground continuity, wire bond or bump transitions, spurious slot line modes, and isolation between drive, flux, and readout pads. Layout must also support frequency allocation and serviceability inside the cryostat. Good packaging reduces loss, crosstalk, and thermal gradients without blocking measurement access. The hard trade-off is density versus isolation. Compact designs help scaling, but can introduce parasitic coupling. Be sure to cover electromagnetic design, package modes, impedance control, grounding, transitions, density versus isolation, thermalization, routing for control, readout lines, and manufacturability at scale constraints. Question 13. When would you use randomized benchmarking instead of quantum process tomography? Randomized benchmarking estimates average gate error by applying random Clifford sequences and fitting the decay in survival probability. I like it because it is relatively insensitive to state preparation and measurement errors. Tomography gives richer process information, but it scales poorly and is sensitive to spam. For hardware debugging, RB tells me whether a gate is broadly good. Leakage RB, unitarity, GST, or Hamiltonian learning can then identify coherent error, leakage, or calibration bias. While answering, compare RB with tomography and GST. Explain spam robustness, average error estimation, scalability limits, leakage variance, coherent error diagnosis, and when each tool is appropriate. Question 14. How would you characterize whether dephasing is caused by flux noise, charge noise, or microwave control noise? If I suspect flux noise, I design experiments that convert noise into measurable dephasing. Ramsey is sensitive to low-frequency noise, echo suppresses slow components, and varying idle time or bias point reveals spectral behavior. I also compare sweet spots against flux-sensitive regions. For microwave amplitude or phase noise, I use repeated Rabi, Ramsey detuning, and mixer leakage checks. The goal is to connect a noise spectrum to a physical source, not just report a shorter T2. Make sure to describe experiments that map noise to dephasing, including Ramsey, echo, bias point sweeps, spectral interpretation, flux noise, microwave phase noise, and source identification. Question 15. How does quantum error correction change the requirements for quantum hardware? Quantum error correction changes the hardware target from isolated good qubits to reliable repeated operations. For a surface code style system, I need high-fidelity, nearest neighbor gates, fast and QND readout, low leakage, reset, synchronized control, and stable calibration across cycles. Connectivity and crosstalk matter as much as single-gate records. I would design hardware around the full syndrome extraction loop, because small correlated errors, leakage persistence, or readout latency can dominate logical performance, even when individual benchmarks look strong. In your answer, connect hardware specs to logical performance, gate fidelity, leakage, reset, QND readout, latency, connectivity, crosstalk, correlated errors, synchronization, and repeated syndrome extraction. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.